Welcome back to Quantum Geology. In this video, we will learn about the physical properties of minerals. Minerals have a variety of physical properties that are key to identifying and classifying them. Apart from the physical properties, minerals have their distinct chemical and optical properties. Important physical properties that characterize a mineral and allow us to separate one from another in hand specimens are the following. Color. In this video, we will discuss briefly about color. Habit. External form that may be prismatic, blocky, bladed. The third one is luster. Appearance of light reflection. It may be metallic, glassy, or dull. Cleavage. Tendency to break along weak surfaces. Minerals with cleavage break in smooth, flat surfaces. Hardness. A measure of how resistant a mineral is to scratching. Mohs hardness scale, ranging from talc to diamond, is commonly used to rank minerals by hardness. Specific gravity or relative density. Specific gravity is the density of mineral relative to density of water. Streak. Color of powder. This is often tested by rubbing the mineral on a porcelain plate to see the color of the streak left behind. Fracture the way mineral breaks irregularly. Tenacity. It describes how mineral responds to stress, such as bending, breaking, or tearing. Terms like brittle, malleable, ductile, and elastic describe different types of tenacity. Apart from this, certain minerals, especially carbonates like calcite, will react with weak acids, hydrochloric acid, by fizzing or effervescing. Now let's understand the color as a physical properties. While color one of the first things we notice, color alone isn't always reliable for identification since it can vary due to impurities. What is color? Color is the response of the eye to the visible light range of the electromagnetic spectrum. Visible light ranges in wavelength from about 400 to 700 nanometers. As we know, white light is a mixture of all these wavelengths. The equation relates the energy of radiation to its wavelength lambda, where c is the speed of light and h is the Planck constant. What this equation shows is that when the wavelength becomes longer, the energy is reduced, and when the wavelength becomes shorter, the energy increases. The electromagnetic spectrum is the range of all types of electromagnetic radiation organized by wavelength and frequency. Each type of radiation in the spectrum travels at the speed of light, but differs in frequency and wavelength, giving it unique properties and uses. Visible light is the only part of the spectrum visible to the human eye, used in lighting, photography, and displays. Colors are differentiated by wavelength, with red at the longest and violet at the shortest. In visible light, frequency determines the color. Higher frequencies correspond to violet and blue light, while lower frequencies correspond to red light. In the electromagnetic spectrum, the higher the frequency, the shorter the wavelength. This relationship is due to this equation. Light interacts with minerals through processes like reflection, refraction, absorption, and transmission, which influence their color, transparency, and unique optical effects such as fluorescence and iridescence. When light hits the surface of a mineral, a portion of it reflects back. The type of reflection depends on the mineral's luster. The color of the reflected light is what gives the mineral its surface color. The color of a mineral is the eye's perception of the wavelengths of light that are either transmitted or reflected by the mineral before reaching the eye. When part of the visible light spectrum is absorbed during its path through a mineral, the part that is not absorbed is responsible for the color. When white light strikes a mineral, it may be scattered or reflected, it may be refracted, and it may be transmitted and absorbed. If almost all of the light is reflected and or scattered, the mineral will have a luster described as metallic luster. This is exhibited by the surface of steel, copper, silver, and gold. Such materials are described as opaque because little light passes into the mineral. Metallic luster is also shown by many oxides and sulfides. For example, pyrite, galena, and hematite are all opaque to light and have a metallic luster. If the incoming light to a transparent, non-metallic mineral suffers no absorption, the mineral will be colorless. If, however, parts of the visible spectrum are absorbed, the mineral will be colored. Most of the reactions that cause light absorption are the result of wavelengths of visible light inside a transparent or translucent mineral and the interaction of that incoming electromagnetic radiation with specific chemical elements housed in the crystal structure. For example, the mineral corundum is normally colorless, but when it contains trace amounts of chromium 3+, it becomes red, known as ruby, and when it contains trace amounts of iron 2+ and titanium 4+, it is blue and is called sapphire. Look at the photographs of the ruby and sapphire. Several major rock-forming mineral groups show specific colors because they have in their structures large amounts of certain chemical elements known as the transition elements. Transition elements have atomic numbers between 21 and 30 and include scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These are also referred to as the chromophore elements, with chromophore derived from two Greek words meaning color-causing. Some of these transition elements, chromium, manganese, iron, are major components, not trace elements, in, for example, garnet, olivine, pyroxenes, and amphiboles. Reasons for color in minerals. First one is crystal field transitions. The presence of transition metal ions in a mineral can cause color due to crystal field splitting. When light interacts with these ions, electrons can be excited from a lower energy level to a higher one, absorbing specific wavelengths of light and reflecting others. This absorption leads to the distinct colors observed in minerals containing transition metals, such as the green of chromium in emerald. Second one is molecular orbital transitions. In some minerals, the color arises from electronic transitions between molecular orbitals. When visible light strikes the mineral, electrons can be promoted between different energy levels in molecular orbitals. The specific wavelengths absorbed during these transitions give rise to the observed color. For example, the deep blue of azurite is attributed to such transitions. Last one is color centers. Color centers are defects in the crystal lattice of a mineral where an atom is missing or replaced by another. These defects can capture and localize electrons, leading to the absorption of specific wavelengths of light. These interactions highlight the complex nature of how color is produced in minerals, making it an intriguing aspect of mineralogy. Now we will discuss one by one. Before going on to understand crystal field transitions, let's brush up on some basic concepts which you already learned in intercollegiate studies. What are transition elements? Transition elements, also known as transition metals, are the elements found in groups 3 to 12 of the periodic table. These metals are characterized by their ability to form variable oxidation states and to form colored compounds. In transition element, there are 5 d orbitals in each d subshell designated in the diagrams. These orbitals have specific shapes and orientations, affecting how they interact with ligands in coordination complexes. In the presence of ions, the degeneracy of the d orbitals is lifted, leading to crystal field splitting. In an octahedral field, the d orbitals split into two sets, E1G, higher energy, T2G, lower energy. The energy difference between these split orbitals, delta, can influence the color of the transition metal complex and its stability. Molecular orbital transitions, also known as charge transfer transitions, occur in minerals when valence electrons transfer back and forth between adjacent ions. The electrons are contributed to shared molecular orbitals and as such are delocalized. That is, the valence electrons of a constituent atom are no longer in atomic orbitals centered on the atom. In such instances, crystal field theory does not apply, but instead molecular orbital theory best describes the observed spectra. Examples of molecular orbital transitions are found in many minerals. Of these, Fe2+, 2Fe3+, and Fe2+, and T4+, are the most common metal-metal charge transfer transitions. In the Fe2+, 2Fe3+ charge transfer transition, an electron is transferred from Fe2+ in site A, making it Fe+, to Fe there plus in site B, making it Fe2+. Energies of this reversible electron hopping process generally correspond to wavelengths in visible light, and many minerals owe their intense blue color to such transitions. In this diagram, the graph for sapphire, blue gem variety of corundum. The absorbance of blue light is at a minimum, so blue is the dominant color we perceive. In the second diagram, the absorbance of green light is the least, so the mineral olivine appears green, while the least absorption of red light in garnet results in its red color. Examples of some common minerals whose color is the result of charge transfer transitions described by molecular orbital theory. The blue color of fluorite is caused by the interaction of electromagnetic radiation with defects in its crystal structure known as color centers. What type of defect do you notice? Frenkel defect or Schottky defect? Write in the comment section. The Frenkel defect is a type of point defect that occurs in a crystal lattice and involves the displacement of an atom or ion from its normal lattice position to an interstitial site. Schottky defect, a point defect involving the absence of a pair of oppositely charged ions from the lattice. Is color a diagnostic property? While color is a diagnostic property, many minerals can exhibit a range of colors due to impurities or variations in their crystal structure. For example, in this slide, you can see the different colored beryl minerals, which are all the same mineral. Play of color, best shown by precious opal. Precious opal consists of amorphous silica in spheres of about 3000 Armstrong diameter with small amounts of water. Look at the scanning electron microscope image of opal with a chalky appearance. These spheres, which are cemented by amorphous silica with a slightly different water content, are stacked together in a regularly packed array. The interaction of visible light with such a regular array of spheres causes diffraction effects that result in a play of color. In the next diagram, you can see how the diffraction of visible light into various colors due to regularly spaced planes caused by the regular stacking of amorphous spheres in precious opal. Chatoyancy. What is chatoyancy? Chatoyancy typically arises from the presence of parallel fibrous inclusions within the gemstone. When the specimen or polished stone is tilted, a narrow beam of light moves from side to side as a result of the tilting. This is known as chatoyancy and is best seen in the sateen spar variety of gypsum. To bring out the chatoyancy effect, gemstones are typically fashioned into a cabochon cut Cabochon cut is a style of gemstone cutting that features a smooth, rounded top and a flat base, rather than the facetted surfaces seen in many other cuts, characterized by a rounded, flat base rather than facets, with the fibrous structures aligned parallel to the base. Labradorescence. It is most pronounced in that part of the chemical series known as labradorite. The iridescence is the result of the scattering of light from a microstructure that consists of a regular pattern of closely spaced, parallel planar lamellae, known as exsolution lamellae, which have slightly different chemical compositions in adjoining lamellae. The scattered light diffracts from these microstructures, producing colors ranging from blue to green, yellow, and red. This is known as labradorescence. Asterism. Asterism is an optical effect that creates a star-like pattern on the surface of a gemstone when viewed under a light source. This effect can appear as a 6-rayed star, although some stones may exhibit 4 or 12 rays. Fluorescence. Fluorescence is the emission of visible light in some minerals as a result of exposure to ultraviolet UV light. Electrons in the mineral structure that become excited by the UV radiation are raised to higher energy levels. When they fall back to a lower, intermediate energy level, they emit visible light with a specific energy and hence a narrow range of wavelengths, which can produce vivid colors. That means, when UV light strikes the mineral, exciting its electrons, the energy absorbed by these electrons allows them to jump to higher energy states. When they transition back to their original or lower energy states, they release energy as light, which is typically visible to the human eye. Phosphorescence is the emission of radiation in a similar manner to fluorescence, but on a longer time scale, so that emission continues after excitation ceases. When phosphorescent materials are energized, for example, by UV light, electrons are excited to higher energy states. In phosphorescence, some of these electrons become trapped in metastable states, meaning they remain in the excited state longer before returning to their ground state. Asbestos. How hazardous is it? Asbestosis, chronic lung scarring, causes breathlessness and coughing. Mesothelioma, aggressive cancer of lung, abdominal lining, almost exclusively from asbestos. Lung cancer and pleural effusion. Thanks for watching. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell so you never miss an update. Your support really helps grow this channel.